In this video I wanted to give you a quick review of how to do a change of bases of a logarithm, or more directly, how to solve an equation with logarithms if you want to use a calculator to help you evaluate the logarithm. So one of the issues that we run into when we're dealing with logarithms is that if we're trying to use technology to help us evaluate or find the values of logarithms, it turns out that most calculators only have two logarithms that you can use by using just one or two keys on the calculator. One is log base 10, where the base is a 10 here. And the other one is called the natural logarithm, which is log base e. E is called the natural number. It's something that arises a lot in calculus and a wide variety of applications. And I don't really want to go into its origin right now, but you might also see a key for log base e, or ln is another notation for the natural logarithm. So you have on the calculator there's probably a button with something like log base 10, or it might just say log, and you might have another button somewhere else that says log base e, or another notation for this is ln, or log of the natural number, log base e. So these are usually the only two operations that we have available to us if we want to use a logarithm or evaluate a logarithm with a calculator. Before the advent of calculators, people used to carry, well, maybe not carry around, but they would look up the values of logarithms in books. You'd have a table of logarithms which would have all the values for any standard base that you might be faced with. It could have log base 2, log base 3, log base 10, whatever you needed to worry about. They would have, there's a table that just had lists of values of the logarithm function. With the advent of calculators and the change of bases ideas, it turns out that we can use just these two operations to help us find the values of logarithms quickly and efficiently. The reason we have these two versus any other set of logarithms is that the natural logarithm turns out to be a function that's very, very useful in calculus. It helps us plug a hole in our theory of integration, as well as reversing the exponential function, which also appears quite often in applications. Log base 10 is important to us because we typically use the decimal number system. And if you look at a decimal number and you take its logarithm, the value of the logarithm will tell you how many digits you have in that decimal number. So that can be a powerful way to see a rough size of how big a number is. Okay, so what I want to do is I just want to show you how to convert one base into another, or really the goal here is to understand how to use these two operations to solve generic equations where you're looking for an exponent, or the goal is to find the exponent. So we know from the definition of the logarithm that it's supposed to cancel out. It's supposed to be the inverse function for an exponential function. So if I have access to log base a, if that's something I'm able to compute, then I can take the logarithm of both sides of an exponential equation, and that will help me solve and find the value of x. If we want to solve an equation like this and we don't have log base a as an operation we can perform on our calculator, then we need some other way to solve this equation to get x by itself in terms of one of the operations that we do have access to. So what I want to do is I want to show you how to convert or evaluate log base a of b using one of these two operations. It doesn't matter which one you use, but you'll want to use the same one consistently. Okay? And the way that we're able to do this, the way that we're able to evaluate the change of basis, is by using the properties of logarithms. Okay? So this is an application of those algebraic properties. So the way that we figure out that change of basis formula is we begin with our exponential equation. So we have a to the x is equal to b. And then we wish to solve this equation for x to get it on one side by itself. So we're going to apply one of the logarithms that we're going to have access to on our calculator to both sides of this equation. So I'm going to use the natural logarithm, so I'll use ln, which is log base e. I'm going to apply that operation to both sides of this equation. So I have log of a to the x power is equal to the log of b. One of the things that we get used to doing is when we start to only use one logarithm and not change the base of our logarithms, we often just say log, or another abbreviation if you're trying to speak this function is just to say ln. This is the ln of a to the x is equal to the ln of b. And this is coming from just assuming that I know a and I know b, and I'm trying to find the power x that makes these two things equal to one another. So we've applied this one step, applied the natural log to both sides, or the logarithm base e to both sides of this equation. And next, the next step that we want to take is to get the x, or move the position of the x so that it's not stuck up in this exponent. And the way that we're going to do that is by using one of the properties of logarithms. So remember that if I have log base, let's say c, of a to the x, any logarithm of a base x, we can think about this as the log base c of a multiplied by a multiplied by a. If x is a nice integer, this is x times, and if x is not an integer, it still generalizes nicely. So we know that what we can do is, if we have a product inside the argument of our log, we can split that into a sum of logarithms. So we can think about this as being log base c of a plus log base c of a x times that, right? So we've got a bunch of copies of that. If we combine them all, we can then bring that exponent down as a coefficient. So the long and the short of this is, the property that we're really trying to exploit is this property that exponents in the arguments of logarithms can become coefficients. They can be brought out in front of the logarithmic term. Okay? Those two things are equal for any a, for any base c, and for any nice real power x. So in this situation, this equation that we're trying to solve for x, when we apply a logarithm to both sides, regardless of the type of logarithm that we use, regardless of the base that we use, we can bring the x down as a coefficient on the left-hand side. So this left-hand side is equal to x multiplied by the natural log of a. That's equal to the natural log of b. Okay? Once we've made that transformation, once we've exploited that property of logarithms, now this is a simple equation to solve for x. It's x multiplied by a number. Okay? So to solve this, to finish this process, we just need to divide by the coefficient of x, which is this number log of a. So this brings us to what's sometimes called the change of bases formula. We find that x is equal to the natural log of b divided by the natural log of a. So that's a formula for the exponent in terms of the natural logarithm operation, not in terms of log base a. But what we can do is think about this process in general, how to evaluate a log with a strange base by using either log base 10 or the natural log. We just remove the x. This expression is equal to x. This expression is equal to x. So we find that log base a of b is always equal to the natural logarithm of b divided by the natural logarithm of a. So if you're trying to evaluate a logarithmic expression and you have access to technology, you can evaluate it using either the natural logarithm, which is an operation that should be in any scientific calculator, or you can just as easily use log base 10 if you have access to that operation. Both should work fine. So you can evaluate log base a of b by taking log base 10 of b and dividing that by log base 10 of a. And the argument there is identical. Take the original equation with a and b known and x being the thing that you're trying to find, and apply log base 10 as an operation to both sides. the property of logarithms applies to log base 10 just like it applied to the natural log. So you can solve this using an identical process. So this is kind of the origin and the purpose of this change of bases formula. With technology, we only have access to a couple of different logarithm operations, but by knowing the change of bases formula, we can compute any kind of logarithmic expression, compute the value of any type of logarithmic expression we wish.